Okay, we're going to start what I believe is the last lecture session of the school. So in this lecture, what we would like to do is to try to essentially do this movie that I was showing you, but ourselves. This is a movie I showed at the beginning of my lectures that shows the evolution of phase space of initially homogeneously distributed density field. Okay, so that is our goal. Let's see how far along we get. So I put on a Slack short PDF with some explanations and also a snippet of a Python code. Do you all have it or not? Yeah. Okay, so. Right, so these notes I put on Slack. So it's just a rough guide to the exercises and some questions for you to think while you do the exercises. Right. So as I was saying, we're going to try to do to write our own embodied code that solves for the gravitational evolution of a fluid in 1+1 dimension, so it's one position and one velocity. So the basic structure of the code is in this Python routine. So I'm going to explain them to you briefly. So you know, so there are first three functions that are defined. The first one is just computes, so enforces periodic boundary conditions. So you can give whatever value of a position, and then it always wraps it to fit into your simulated domain. Then the second one does the same, but for distances. So you give position A and position B, and this function is going to compute the distance, taking into account also periodic boundary conditions, just helper routines for you. And then the next one is acceleration. That is a function that we will have to write. So this is going to receive as an input the positions of the particles that you're going to be simulated. And so the first task is to take that as an input. The positions is an array with the position of n particles. And we need to return the force or the acceleration that each of these particles feel. Right? So that is going to be the first task. And right. And below there is the main structure or the main loop of the code. So first we set a couple of parameters, the box size, the amplitude of the fluctuations, the maximum, the final time, the number of time steps that we're going to use for evolving your system, and so on. And then in lines 67 and 68, we're creating our initial conditions. So line 67 is a uniform distribution of particles between 0, whose positions are uniformly distributed between 0 and box. And then we have number of particles is as an input parameter. And then the velocity is in this case given by an amplitude times a sine of 2 pi over the box size times L. So we have a sinusoidal fluctuation that just covers the whole box. Right? Then we have some functions, some routines just to display the main results. And then comes the main loop in around lines 80. And there we have to fill and write our own symplectic time integrator. Right? So this is what we went through the lectures, and the equations are written in the code and in the notes. Okay, so then we have to fill this integration, and then we run the code, and we should be able to visualize the phase space evolution of this initially sinusoidal wave, and then we're going to try to see what happens. So, are there questions? Did I went too fast, or is it clear? more or less, no? You want to start? Well, so you can start looking at the code. So the first task is to fill the acceleration function. Remember, take an input array, and then you have to return the force. Right? So the force is just the sum over all other particles, and you sum 1 over distance squared that's in 3 dimensions. And well, you can play actually with the dimensions that you want to compute gravity in. Okay, let's start with that. You can raise your hand if you have any questions, and then I can get close, and then, well, we can, in 10 minutes or so, 15 minutes, we can, or are there any questions right now? Do you guys know what to do, or? Yeah, sorry? Repeat the. So what do you have to fill? So it's at the beginning of the Python script. It's around line, it's actually at line 21. It's a function called acceleration, and receives as an input an array of the positions of the, or it's an array with particle positions. Right? It's a dimension, it's a single vector that just gets the position, right? So now you have to compute for every of these particles the acceleration that those particles will exert, right? So we know that, so we are going to receive as an input a vector x. So we have to compute what is x double dot, right? And we know that it's simply, well, a proportionality constant, but let's just do this, assume that assuming g equals 1, that's going to be the sum of all the particles where, so the acceleration for particle I is going to be a sum over all particles where j is different than I, so you don't exert force onto yourself, times essentially the distance between particle I and particle j. Sorry, so this like this, and then the modulus j would be cubed, or actually would be number of dimensions minus 1, right? Where d should be 1 dimension, or you can, so it's like that. Okay? So over the dimensions. So we can play with the dimensionality of our problem. We have 1 dimension, this 1, or if you take gravity in 3 dimensions, this coefficient would be 3, and so on. Right? So but let's start by, essentially, this would be what we need to implement. Right? This is going to give us the acceleration to the particle j. So we need to do that for every particle. Right? And this is what the function acceleration should return. Yep. Okay, so, well, you can start having a go, and then ask me if you have any questions. By the way, you might have troubles with the fifth line, the IPDB. So you might not have it installed. So you can. It's not necessary for anything. So you can just delete it in case you run into problems. Okay, who has managed to I mean, does everybody understand what we are trying to do? Or any questions about that? Yes? What is X? That was an array with the positions of all particles. Right? So that's what the function was getting as an input. It's like a vector with the positions. If you have 100 particles, then it's 100, the vector of 100 dimensions, and then it has the actual position for each of these 100 entries. Okay, so who has managed to finish this function? Yes, one person. Okay, so so here I was writing what I meant. Maybe I was not clear enough, right? So now we have to compute the acceleration. So now what we do is do a for loop over all particles, all this input array, and now we get the position and the actual value. And now the acceleration then that this particle feels is going to be the sum of the difference of that position minus all the array over the same distance, the absolute value to the power of the dimensions, right? So there are a few things here that are not quite correct though. So the first thing, we need to account for periodic boundary conditions, right? So now we actually, because you can imagine that if you have a particle at the extreme, at the edge, have one particle here, for instance, this is your domain, and now you have another particle here, right? So which distance should you take? If you imagine that you have periodic boundary conditions, this particle is actually also here, right? So the whole thing is repeated multiple times, right? So we actually take the distance that is the closest between all possible replications. So that is what this periodic distance function does. So now we take this distance between x and x2. Right, so now we have the distance. So now we can sum over the distance and the absolute value of the distance to the power of the dimensions. Let's take dimension 1. Right? So there is another problem that this equation still has the self force, so we need to avoid the I equals, so essentially you're all particles, so we are going to do the sum, but with a mask, where all the indices, or all the positions where the indices is different than I. Right? So now do this. and we have our function. Yeah. Does it make sense? Okay, so now this is a more complete version where we also take into account the effect of the softening length. So now we modify, you remember what we were discussing, that when we have particles that get close to each other, the force diverges, so we need a regularization parameter. So we change our Newton's law, or by a modified version in which we essentially do this. Is this xi minus xj squared plus epsilon squared and a square root of all that. It's minus 0.5. Right? So now this is what I have written there. Okay. Questions about this? Okay, sorry, I had made a, there should not have been minus, it's times 0.5. Okay, so do you all have now the, is a question? What is what, sorry, cannot hear. The M part? The range? Right. Okay. So that is a NumPy function that creates a sequence of numbers 0, 1, 2, 3, 4, 5 up to the argument, which in this case is the length of that input vector. So if we have 100 particles, that indices will be a vector that goes from 0 to 99. So tells us comes the position in the array. So now we can use it to make a mask and take away the distance that to yourself, right? That is this line of indices different than I. Right? So then we don't account for kind of self force. Okay, so we have the. So do you all have the force implemented? Or do you need more time? No? Okay, so we can go then to the next part, which is to do the time integration. Right? We were saying it is in the main loop. So now we have to implement our Leapfrog integrator, which is the first position at plus half a step. should be the previous position, xi, plus half delta t times the velocity at I. And the next line, we update the velocity. Now we can use a full step. And now the acceleration is the function we just computed. As an input, the positions evaluated at x at I plus half a step. And then we do the second half step for updating the positions. So it's the position plus half plus 1/2, or I plus half, is delta t over 2 times the velocity we just computed.